Good morning, good afternoon, good evening, everybody. Today I'm going to talk about SPE 204282, which is the scale control for long-term well and facility preservation. This was written by a few folks from Chevron, and the authors are listed below. The objective is to review and assess the scale risk for different scenarios for the operation shut-in periods and utilize lab studies to improve the understanding of long-term impact and identify appropriate mitigation strategy. Here's an introduction of the well shut-in operations, commonly applied in oil and gas for various reasons, and here are the timelines and examples that have been summarized in the three categories. You have your short-term shut-in, which is applied for chemical application such as after-scale inhibitor squeeze treatment and for shale, and tight after fracturing to avoid frac hits. For pipeline hydrostatic testing, a 24-hour shut-in time is usually required. This shut-in process is commonly lasts for hours to days. You have a medium shut-in, where it's commonly applied for deep water wells during repair, routine maintenance, and extreme weather change. Cyclic shut-in are put onto production to curtail production. This process could last from weeks to months. Then you have a long-term shut-in. This is a well shut-in due to war or civil upset on political uncertainties, wells for permanently abandoned. This process could last for months to years, or a permanent well shut-off. Here's a methodology for this work. They simulated brine comparisons for both conventional and unconventional fields, commercially available scale inhibitors used for testing. Various conditions, including temperature, saturation index, and ratio of scaling ions are evaluated. They tested the inhibitor dosage and range from 0 to 3 milligrams per liter. And the inhibitor brine compatibility was also tested. Sulfate and carbonate scales such as barium sulfate, strontium sulfate, and calcium carbonate are studied as an example. And the performance of two scale inhibitors for the same water composition are demonstrated. Synthetic brines have been used for the test. Overall ion concentrations are higher in area 2 with higher pH value, and you can see that in the table on the left. All tests have been performed at 74 degrees C and 1 bar in a sealed glass bottles over a period of 14 weeks. 2 commercially available scale inhibitors, inhibitor 1 and 2, were used, and both are phosphate-based chemicals. 6 inhibitor concentrations were used. Bottles have been visually checked twice per week to determine if precipitates were formed. Then I'll talk about the long-term evaluation for inhibitor performance. Synthetic brines have been used for these tests. Produced water composition was used to represent formation water. Scale saturation index and amount were modeled with SSP to find the mixing ratio of formation water and frac water, which could lead to the highest scale risk during fracking. All tests have been performed at 74 degrees C and 1 bar in a sealed glass bottles for a period of 22 weeks. Scale inhibitor 1 and 2 were also used with a dosage from 2 milligrams a liter to 250 milligrams a liter. And then bottles have been visually checked twice per week to determine if the scale was formed. Now I'll talk about the long-term evaluation for psudoscale formation and inhibitor performance. Synthetic brines were used for these tests. Various parameters have been adjusted to evaluate their effects on pseudoscale formation and their inhibitor performance, including barium sulfate ratio or barium to sulfate ratio, pH, and temperature. Inhibitor 3, currently used for scale control at deep water locations, was applied to represent as a conventional scenario with the concentration from 2 to 150 milligrams per liter. All tests last for 7 weeks. Bottles have been visually checked twice per week to determine if precipitates were formed. Now I'll talk about some extensive results from the long-term scale inhibitor testing. Different mixing ratios of produced water from areas 1 and 2 with frac water have been evaluated to mimic the scenario, which was a higher scale risk. For area 1, at 50% produced and 50% frac water mixing has been chosen, and for area 2, 40 to 60 produced to frac water has been chosen for a long-term test. Modeling results from Area 1 suggested a moderate scaling risk for both calcite and celestite. For Area 2, moderate to high scaling risk for calcite and moderate scaling risk for celestite. And that is shown in the tables 2 and 3 to the right. There was no precipitate observed for inhibitor 1 at 150 and 250 milligrams per liter dosage after 24 weeks, indicating that there's much higher performance than that of inhibitor 2. The 250 milligrams per liter of inhibitor 2 have protection time for 16 weeks. Both curves have similar trend but do not follow a linear correlation, which has been observed for short-term inhibitor performance for the entire dosage range. Inhibitor performance has a sharp increase from 2 milligrams to 20 milligrams per liter. There's a clear transition section from the 20 to 50. Inhibitor during the increase of protection time slows down. From 50 to 250 milligrams per liter, the protection time steadily increased with dosage. And that is all shown to the tables to the left. The short-term stage has been proven to have a linear correlation by previous research. The poor R-squared value shown is due to the low resolution of sampling frequency, which is targeting during the long-term period. Transition stage at the 20 to 50 milligrams per liter inhibitor in this case could have had a different starting point in the scenarios with various scale risk potential and using different inhibitor product. The long-term stage shows a linear correlation which could be used to predict inhibitor protection time and compare inhibitor performance. If the protection time of the blank test are known, it is practical to predict and estimate the protection time with higher inhibitor dosage without performing long-term testing. Protection time for all 4 cases reported at 50 milligrams per liter and 100 milligrams per liter for 4 to 16 weeks. If time allows, the long-term tests are still recommended. Long-term stages for Area 1 and Area 2 have been overlaid to compare the inhibitor performance. Inhibitor 1 overperformed inhibitor 2 for both scenarios. The predicted protection time at 150 and 250 milligrams per liter of inhibitor 1 for Area 1 is 21 and 38 weeks respectively. That's all shown on the tables to the left. So Area 1 is to the left and Area 2 is to the right. Now we'll talk about the inhibitor-rock reaction. Inhibitor 1 has largely been absorbed in all 3 cuttings regardless of rock mineralogy. Inhibitor 2 shows a different absorption rate for the 3 cutting samples. More than 90% of added inhibitor 2 were absorbed by shallower cuttings for deeper locations, and 48% of inhibitor 2 was absorbed. This could be due to the inhibition of water during the rock soaking under test condition. The formula difference for these 2 inhibitor products could also contribute to the absorption behavior. Among the tests, quartz clay-rich rock has lower absorption rate for inhibitor 2. You can look at the mineralogies from the QXRD results for the 3 cutting samples of Area 1, and then you can look at the absorbed cutting examples for different depths between inhibitor 1 and inhibitor 2 to the plot on the right. Now I'll talk about the long-term evaluation for pseudoscale formation and inhibitor performance. Inhibitor 3 incompatibility issue with the matrix brine when the dosage is from 50 to 150 milligrams per liter. pH and temperature have large impacts on pseudoscale induction and time. When the temperature increased from 77 C or decreased from 77 C to 55 C, the induction time increased from 42 to 56 days at 50 milligrams per liter. The results indicate the increase of pseudoscale solubility with the temperature decrease. On the other hand, decrease in pH from 8 to 7 accelerate formation of pseudoscale. The induction time at 50 milligrams per liter decreased from 42 to 21 days. The change of Ba to SO4 ratio has little effect on induction time. Try to move my slides. So the result summary is that the efficiency of scale of inhibitor 2 is lower than that of inhibitor 1. A linear correlation is observed for long-term scale behavior in performance in this case. Protection time is thus predicted from area collected from the first 8-week experiments, and the predicted protection time at 250 milligrams per liter of inhibitor A and B is 100 weeks and 16 weeks respectively. Here's some conclusions and future work. There's more advanced semi-empirical model for scale inhibitor performance could be developed. And it's important to consider various factors which could affect chemical performance during shut-in. The dosage of inhibitor is affected by brine and chemical compatibility interaction between inhibitor and solids, as well as inhibitor protection time. Cost of chemicals is another important factor influencing inhibitor selection. Long-term protection time in inhibitor could be estimated and projected based upon the experimental results from blank tests and first couple of tests with lower dosages, depending on the scaling risk and scale amount performed. Reasonable linear correlation for higher dosage has been observed for phosphate-based scale inhibitor in the study, which could be expanded to polymeric scale inhibitors. Considering the effects of many factors which could affect the inhibitor performance, inhibitor dosage could be optimized to efficiently prevent scale formation during shut-in scenarios to save your OpEx costs at the same time. That's the conclusion of the presentation. Once again, I hope you guys could like this video, subscribe so you can get more content in oil and gas and professional development topics, and please comment on the video on the YouTube platform so I can incorporate your feedback into future videos. Thanks so much for taking the time to watch this video. I'll see you in the next one.